everyone. I am Praveen. In this topic, we are going to see about free vibrations in continuous system. First, Rayleigh's method for approximating the fundamental frequency of a continuous system. Rayleigh's method is used for obtaining an approximate fundamental frequency for an undamped continuous system, commonly applied to vibrating beams like cantilever beams, for example. Let's assume simple harmonic motion U is equal to V of x cos omega t. First, fundamental frequency omega is approximated using Rayleigh's method. In Rayleigh's method, it was observed that energy conservation in Rayleigh's approximation balances maximum kinetic potential energy, kinetic and potential energy to approximately fundamental frequency. Assumption is maximum kinetic energy is equal to maximum potential energy. The equation for that is T max is equal to V max. For a cantilever beam, strain energy due to bending can be calculated as V is equal to half integration of 0 to L EI is nothing but fractional density EI into psi double dash whole power 2 into dx plus half kT into psi whole power square. Kinetic energy of the cantilever beam with distributed mass. The equation for that is T is equal to half integration of 0 to L rho A psi square dx plus half mt psi whole square, where the rho represents density, A is equal to cross sectional area, and M represents the point mass at xt position. Substituting T max and V max expressions, the Rayleigh's equation, Rayleigh's coefficient is derived by substituting T max and V max expressions. The derived equation is R of psi is equal to omega is equal to square root of k by m. The formula for k by m using shape function, psi of x is equal to x by L whole square for the cantilever, and to calculate k and m using this shape function, psi double dash of x is equal to 2 by L square. The formula for k and m are given. Using shape function, psi of x is equal to x by L whole square for the cantilever beam. To calculate k and m using this shape function, k is equal to 20 EI by L cube, m is equal to rho AL by 5. Psi double dash of x is equal to 2 by L square, the second derivative of the shape function. Substitute k and m to find the approximate fundamental frequency. Omega is equal to square root of 20 EI by rho AL. Or in simpler form, f is equal to 4.472 by L square root of EI by rho A. The exact value of omega is provided for comparison. The Rayleigh's method typically gives an upper bound to exact fundamental frequency. The equation for that is omega is equal to 3.516 by L square root of EI by rho A. In conclusion, Rayleigh's method provides a practical approach to approximate fundamental frequency, useful for systems where exact solutions are difficult to obtain. In this example, it approximates the natural frequency of an cantilever beam. Conversion to beam theory and its boundary conditions. Application to simple supported beams. Boundary conditions of a simply supported beams. One is geometric boundary condition, that is u of 0, t is equal to u of L, t is equal to 0, and the natural boundary condition is alpha dash of x, 0 comma t is equal to alpha dash of L comma t is equal to for free vibration alpha dash is equal to u dash minus rho divided by kg u double dash. Differential equation governing beam vibration is ei dou power 4 u divided by dou x power 4 plus rho into a dou square u divided by dou t square minus rho into a into r power 2 into 1 plus e by kg into dou power 4 u divided by dou x square into dou t square plus rho square into a r square divided by kg into dou power 4 u by dou t power 4 is equal to 0. Harmonic motion as something. Let's assume harmonic motion is u into u of x comma t is equal to v of x cos omega t. Substituting into the equations of motion is alpha dash is equal to v dash minus rho omega square divided by kg into v in equations with harmonic motion. Boundary condition for harmonic motion is v of 0 is equal to v of L, that is equal to 0. The derivative of boundary condition is v double dash of 0 is equal to v double dash of L is equal to 0. Using the beam mode shape equation, mode shape expression is v of x is equal to c into sin n by x divided by L. The solution satisfies the boundary condition yielding a characteristic equation. The characteristic equation derived from the boundary conditions is pi by L whole power 4 plus lambda power 4 into r square into pi by L whole square into e by kg plus lambda power 4 is equal to 0. Correction due to shear and rotary inertia. Discussing the effect of terms in the characteristic equation. Approximate solution considering correction is lambda power 4 is equal to pi by L whole power 4 into 1 by 1 plus r square into pi by L whole square into 1 plus e by kg. Summary of the effect of shear deformation and rotary inertia on beam vibration. The importance of correction due to shear and rotary inertia as the mode number increases. Applicability in structural and mechanical engineering and the properties of continuous system. The properties of modes of continuous system are scaling, orthogonality, and expression theorem. Introduction to natural modes of continuous system. Continuous systems can vibrate at specific natural frequency. Mode shape correspond to these frequencies and have unique properties such as normalization and orthogonality. Analyzing these properties help in understanding vibration patterns of structures, for example, beams. The equation for beam vibration to natural modes of continuous system. Continuous system can vibrate at specific natural frequency. Mode shapes correspond to these frequencies have unique properties such as normalization and orthogonality. Analyzing these properties helps in understanding vibration patterns of structures such as beams. Beam vibration equation for an Bernoulli-Euler beam. E into dou power 4 into B dou power 4 B of x comma t divided by dou x power 4 plus rho into A dou square B into dou square B of x comma t divided by dou t square is equal to 0. E represents the modulus of elasticity. Homogeneous boundary conditions. Boundary conditions specifically constraints at boundaries of the beam. For example, fixed n v of 0 is equal to 0 and v dash of 0 is equal to also 0. Free n e into I v double dash of L is equal to 0 and the e into I v triple dash of L is equal to 0. Example of conditions. V of 0 is equal to 0, v dash of 0 is equal to 0 at x is equal to 0. Ei into d power 2 d square v divided by dx square is equal to 0, comma ei into d power 3 v divided by dx cube is equal to 0 at x is equal to l. Scaling, that is normalization. Scaling or normalization assigns as amplitude to each mode shape. Three standard methods for scaling. First one, set amplitude at a specific location. Scale such at second one, scale such that the maximum amplitude equals 1. Use the third one, use the generalized mass for scaling. The equation for generalized mass for scaling is m is equal to integration of 0 to L rho into A psi square dx. You see the relationship between natural frequencies and scaling. Modes can be scaled to unique natural frequencies labeled as omega I. The relationship between stiffness k and mass m is determined by the natural frequency. The stiffness equation is Ki is equal to integration of 0 to L Ei into d square psi I divided by dx square whole power 2 into dx. The natural frequency, that is omega I whole square, is equal to Ki divided by mi. Orthogonality of modes. Orthogonality ensures that modes with different frequencies are independent. Orthogonality applies to both mass and stiffness disruptions. Mass orthogonality equation is integration of 0 to L rho into A into psi I into psi j into dx is equal to 0 for I is not is equal to j. Stiffness orthogonality is represented as integration of 0 to L Ei into d square psi I divided by dx square into d square psi j divided by dx square into dx is equal to 0. For that also I is not equal to j. Proof of orthogonality property. Detailed derivation of orthogonality property based on integrating by parts. Subtraction of mode equation for distinct frequencies shows orthogonality equation. That is integration of 0 to L rho into A psi I into psi j dx is equal to 0. For I, that is not equal to j. Let's see the expansion of theorem for continuous system. Any function of v of x meeting the boundary conditions can represented as a sum of orthogonal modes, useful in approximating complex vibration patterns. The equation for series expansion is v of x is equal to summation of j is equal to 1 to infinity cj into psi j of x. The coefficient is cj is equal to integration of 0 to L v of x into rho into a into psi j of x into dx divided by integration of 0 to L rho a psi j whole square of x into dx. This cj is calculated and then substituted into that form. The Rayleigh's quotient provides an estimate for the fundamental natural frequency. It derives by assuming a function shape similar to fundamental mode. The equation for Rayleigh's quotient is R of V is equal to integration of 0 to L Ei d square V divided by dx square whole power 2 into dx divided by integration of 0 to L rho a v square into dx. Rayleigh's quotient approximation. When higher modes are ignored, the Rayleigh's coefficient simplifies to fundamental frequency. The equation for that is R of V is equal to omega 1 whole square. free vibrations of thin plates, thin flat plates. The overview of vibration modes and frequency in thin plates, specifically rectangular plates, under various boundary conditions. Let's see about thin plate vibration. The overview for this is thin plates are common in structural system and the vibration characteristics are essential in engineering applications. These are the definitions for thin plate and neutral. Classical small deflection theory of flat plate. Theory basis is based on Kirchhoff's love plate theory, which assumes first one, the middle plane remains neutral, and second one, transverse deflections are small. The third one, points on the middle plane remains perpendicular to the deformed natural plane. Fourth assumption is material is isotropic and linearly elastic, and fifth assumption is shear stresses in the transverse direction are negligible. The equation of motion is further is d into delta power 4 omega plus rho into h rho square omega by rho t square is equal to 0, where the w of x comma y comma t is represents the transverse displacement. D is to calculate the d, the formula is here, and the E represents the modulus of elasticity, and the H represents the plate thickness, P represents the Poisson's ratio. The boundary conditions for rectangular plates. Boundary conditions for a rectangular plate from simple supported clamped and free edges. Example for simply supported plates, that is for x is equal to 0 and a and y is equal to 0 comma p. Omega of x comma 0 comma t is equal to omega of x comma p comma t is equal to 0, and omega of x 0 comma y comma t is equal to omega of a comma y comma t is equal to 0. Solution for the equation of motion. Separation of variables, that is assumes the solution of the form where omega of x comma y comma t is equal to w of x comma y into cos of omega t. Substituting into the equation of motion leads to the eigenvalue equation, that is del power 4 into w minus rho into h omega square divided by t into w is equal to 0, where lambda power 4 is equal to rho into h into omega square divided by t. Mode shapes and natural frequencies. Spatial function w of x comma y is equal to sin c into sin m pi x divided by a into sin n pi y divided by b. The m and n are mode numbers in x and y directions. Natural frequency equation is omega m comma n is equal to pi square divided by a square into square root of d by rho into h into m square plus n square into a square divided by b square. Nodal patterns and mode shapes. Explanation of nodal shapes. Different combinations of m and n yield different distinct mode shapes. Nodal lines. Point where no transverse displacement occurs, visualized as lines or shape on the plane surface. Example pattern from figures are given. Conclusion is understanding the vibration of thin plates is essential for predicting structural behavior in engineering design. Application for this method is used in areas like aerospace, civil engineering and mechanical components. Thank you.